everyone, I am Miss Hu, your physics teacher. In this video, we're going to go through the topic on sound waves. This topic is in both the SPM as well as IGCSE physics syllabus. Now, this video will only be covering a general overview of this topic. There's a lot more to know. So if you'd like to find out more, please feel free to do your own additional research. What we're going to be covering in this video is just the general information that you would need in order to answer the questions in your examination. Without further ado, let's begin. Let me first get my face out of the way. So, what we'll be covering in this video would include how sound is produced, the characteristics of sound waves, the speed of sound, range of audible sound frequency, how amplitude and frequency affect sound waves, as well as the uses of sound waves. Now, you'd also need to know how to do some calculations involving the speed of sound, but that will be covered in a separate video. So please click on the link at the end of the video to watch how you can solve questions using the speed of sound. Now, first of all, let's begin. Let's start off first with how sound is produced. Now, if you can recall what you have learned about waves in general, sound is a wave, and waves involve the oscillation or vibration of the wave in order to transfer energy from one end to another end. So in this case, sound is produced by vibrating sources. So for example, if we're speaking, what happens is our voice box over here will vibrate, and that vibration will be transferred to air, which then carries that energy out so that you can pick up that sound and hear what the person is saying. So for example, over here, I've got a couple of vibrating forks. No, sorry, not vibrating forks, tuning forks. Let me just make my face bigger again. Not for my face, but to show you the tuning fork. So now let's say we've got these tuning forks here, right? Now, if we were to make a sound, what happens here is that the tuning fork is actually vibrating to create that sound. The vibration is a little bit at a high speed, so you can't really pick it up on camera. But if you have a tuning fork and you strike it, you can actually feel that vibration. So even while you're speaking, as you're speaking, just place your hand on your throat and you can feel your voice box vibrating every time you speak. So in general, that's how sound is produced. So all sounds are produced due to the vibration, and that vibration produces that sound. Okay, let's make my face smaller again. Now, another thing you must remember is that sound is longitudinal. So all longitudinal waves, the particles oscillate parallel to the direction of wave travel. So if the wave was traveling from left to right, what happens is the particles are going to vibrate also left to right. So if you recall, all longitudinal waves, they're made up of a series of compression and rarefaction. So the compression area is where the wave particles are closer together, and rarefaction is when the particles are further away from each other. So compression, the particles here are under higher pressure, while rarefaction are under lower pressure. So if we have the slinky spring to demonstrate again, which you should have learned when you first learned about the different types of waves. So what happens is longitudinal waves, they're behaving this way. So the oscillation of the particles here are parallel to the direction of the wave travel. Sound waves transfer energy exactly the same way. That means that if sound was traveling through air, for example, the air particles are undergoing compression and rarefaction as they're transferring energy from one end to another end. So the air particles are doing this. Okay, so the sound waves are undergoing compression and rarefaction, and the particles are oscillating or vibrating parallel to the direction of wave travel. Okay. So one of the confusing things that a lot of students go through, they always thought, hey, but how come then the graph shows the sound this way? Doesn't that make sound transverse? Because if you recall what you've learned about transverse and longitudinal waves, transverse waves have the sinusoidal shape, longitudinal will be this shape. Let me do it again. Okay, sinusoidal wave. Okay, so the thing is about wave graphs is that they're graphs. So the wave graph may look like sinusoidal waves, but actually what happens is it's just a graphical representation of the change in amplitude. So the actual movement of the particles transferring sound waves, let me move my face out of the way. You can see here, right? Now, if you look at the speaker is always dum, 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 because actually what happens is if the speaker is here, it's pushing and pulling the air particles. So that's why you get this kind of motion. So that's why sound is actually longitudinal. Speakers are doing this way, doing this way. They're moving this way to push and pull the air particles so that they undergo compression and rarefaction for that transfer of energy. So what exactly are the wave graphs showing then? The wave is just showing the change in amplitude. So to help you visualize this, again, let's look at the what they call the slinky spring. Now imagine if, let's say, you have a pen stuck in the middle of the slinky spring, and then you've got a piece of paper where the pen is going to draw. So if you were to shake the spring, so the pen's going to be doing this, right? And if you have a piece of paper here and you move the paper, you'll get that sinusoidal shape thing. So then you flip it, that's where you get the chick, 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 chick. So the wave graph is just basically graphing the movement of that particle, like that pen just now. Again, the pen. So it's actually drawing that out. That's how you get that wave graph. So it's just showing you the movement of that particle with time. So it's showing you the change in amplitude over time. And that's how you get the wave graph. So the wave graph is just to graph out the amplitude of the wave. So it's not the actual movement of the wave. That's why sound is not transverse, even if the graph looks like transverse. No, that's just the graph. Based on the actual movement of the sound wave particles, they're longitudinal. So I hope that clears it up a little bit. Another thing you need to know about sound. Sound needs a medium to travel. So waves that need a medium to travel are known as mechanical waves. This means they cannot travel through a vacuum. You should have had this opportunity to observe this in your school lab. If you have the bell jar experiment, well, not you, the school lab should have it. The bell jar experiment is quite simply this. There is a bell connected to a circuit, and the bell is inside a glass jar, which is airtight, sealed and airtight. Now, what happens is when we switch on the circuit, you'll see and hear the bell ringing, ding, 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 ding. Now, this bell jar should then be connected to a hose. So the hose is over here that's connected to a pump. And what happens is the pump, when you switch it on, will start removing air from the inside of the bell jar. So because the jar is made of glass, it doesn't compress easily. But what happens is the air has been removed, leaving a vacuum on the inside. And as the air starts being pumped out, you'll start to hear that the sound gets fainter and fainter because there's less and less air particles. And it'll come to a point where you hear absolutely nothing, but you can actually see the hammer hitting the gong. So that means that the bell is still working, it's still trying to make a noise, but you can't hear anything because there's no more air inside the bell jar. This proves that sound needs a medium to travel. So in this case, sound makes use of the air particles to transfer the wave energy. If you haven't had the opportunity to watch this in real life, I don't have a bell jar, so I can't show this to you. But I'll be happy to put a link where you can watch a YouTube video of some lab demonstrations which show you the bell jar in action. In the meantime, let's move on. Now, you also need to know the range of audible sound frequency. Audible sound frequency here refers to the sound frequency that human beings can hear. The audible sound frequency, as we know of, as of today, is 20 to 20,000 hertz. This is the sound frequency which should be able to be heard by all humans under the age of 25. The older we get, the smaller the range of frequency we can hear, because the older we get, the less flexible the membrane of our eardrums are. So when you start to reach 30s, 40s, you'll start to hear frequency becomes less and less. Yeah. So that's why you'll find that younger people can actually hear quite a wide range, can hear very high sound frequencies, while the older folk, sometimes, the younger folk will be, oh my God, what's that loud? That's irritating sound. And the older folk will be like, huh? I don't hear anything. Yeah. Okay. So the older we get, the lesser our hearing range would be. But anyway, for your examination, you just need to know this. The audible sound frequency is between 20 to 20 kilo, well, 20 hertz to 20 kilohertz, or specifically 20 to 20,000 hertz. The sound frequencies that lie below this range, that means below 20 hertz, they're known as infrasonic or subsonic sound range. While those that are above the 20,000 hertz range, they're known as ultrasonic or supersonic sound waves. Now, let's talk about the speed of sound. Because sound needs a medium to travel, obviously, the speed of sound will depend on the medium that it is traveling through. So, if the medium changes, the speed of sound is also going to change. Now, let's first of all understand the difference between the three states of matter. So, solid particles are right next to each other, liquid particles a little bit further, while gas are even further apart. So speed of sound in solids are the fastest, followed by liquid, and the slowest in gas. So most people think, oh, it's the fastest in air. Sorry, no. Okay, in solids, they're a lot faster because the particles are right next to one another. So what happens is that it's easier for the particles to transfer energy. Liquids a little bit further, so it takes more effort and more time to transfer the energy. Gas is even further apart. Get my hands. Okay, further apart, so it takes more time to transfer the energy. Right? It's not about density in this case. No, it's about the placement of the particles because solid particles are right next to each other. Okay, much faster. Okay, not about density. Some of my students thought, oh, is it because solid has higher density, it travels faster? No, no, no. Density can actually slow down the speed of sound. Yet, how come solids, even though it's higher density than liquids and gases, can transfer energy faster? It's not because of density. It's because of the position of the particles. Here's a video to help illustrate the transfer of sound wave through solids, liquids, and gases. So this is an excellent animation. So here we have we find in this animation they use the animation of dominoes to show how the sound wave can transfer quickly through the particles of solid compared to liquid and gases. So let's watch that. Okay, so this shows you very clearly how come sound can travel so much faster through solids compared to liquids and slowest in gas. Okay. Also, if the temperature of air changes, that can also change the speed of sound. So in hot air, the speed of sound is much higher than in cold air. Now, unfortunately, I haven't found a way to make the particles move about yet, but here's the reason why speed of sound is faster in hot air. Think about it. Hot air, cold air, the particles, which one are going to have more kinetic energy? Hot air, right? So because it's moving a lot faster, it transfers energy a lot faster. Cold air is like a bit slower, so it takes. So that's why you'll find that the speed of sound in hot air is a lot faster compared to cold air. In terms of how sound properties can change, you should know that amplitude affects loudness while frequency affects pitch. So amplitude means, how high the wave particle go, how much. Okay, so the higher the amplitude, the louder the sound would be, right? Because if you recall what you've learned about waves, amplitude is affected by the amount of energy. So the more energy the wave has, the higher the amplitude. So logically, if sound has more energy, higher amplitude, it's louder. Frequency, on the other hand, affects pitch. That means a higher frequency, higher pitch, lower frequency, lower pitch. Please remember that these two values are independent of each other. Amplitude does not affect pitch. Frequency does not affect loudness. So you can have different sound waves with the same frequency but different amplitude. That means different pitches, same loudness. While you can have sound waves with the same amplitude but different frequency. So that means, did I just say that? They can have different amplitudes, same frequency. So that means the same note but different loudness. So just to demonstrate this again, we're going to use the tuning forks. So for example, okay, we have two different forks. Let me get another two that's far more different. So you've got this tuning fork and you've got this tuning fork. Ooh, let me swap it for your view. Okay, we've got the shorter one and the longer one. So these have two different lengths. So that means they have different frequencies. So when I strike it, so let's say same tuning fork, I strike with different amplitudes. So it's very soft, much louder. Or you can have two different tuning forks with the same loudness. Different sound. So you can strike them both with the same strength, so they have the same loudness, but they sound different. So same amplitude, different frequencies. Or you can have the same tuning fork, strike them soft, strike it loud, same frequency, different amplitudes. Now, graphically, to understand this, again, let me move my face out of the way. Okay, so in order to be able to interpret, and you need to know this for your examination, right? You can see here, this graph has a lower frequency, therefore lower pitch. This graph, higher frequency, therefore higher pitch. If you compare these two, they have the same amplitude, so they have the same loudness, but they have different pitches. These two graphs, on the other hand, they have different amplitudes. You can see this has a lower amplitude while this has a higher amplitude, but the frequencies are the same. You can see here you've got 1, 2, 3 waves, 1, 2, 3 waves in the same amount of time, so they have the same frequency, yet they have different loudness. So same pitch, but this is louder than this. So when it comes to understanding the graphs, you need to know how to read the frequency and amplitude in order to interpret whether it's a higher or lower pitch, or is it a louder or quieter sound. Some of the applications which you need to know for sound waves. So because sound waves, they're not very destructive. Okay, not very. Okay, very loud, yes, maybe, or very high frequency, maybe. But generally, sound wave is not very destructive. So they can be used for non-destructive testing of materials. You can also use this for medical scanning of tissue, which is normally known as ultrasound, to find, the rough position and shape of the baby, or even for detecting the not detecting, but to take a look at what's on the inside of your tissue and your organs. Also used for sonar detection under the sea. Now, how all these work is actually based on sound reflection, because what happens is these devices, they will send out the sound wave, and then when it hits a surface, it reflects back. So that means these devices have both the transmitter and receiver. So it can transmit the sound wave and also receive the sound wave in order to figure out, okay, where the position of whatever you're looking for is. Because the further away, the longer the time. So you see, this is the sound transmitter, receive very fast. But if it's further away, it takes a longer time to receive. So these devices have both the transmitter of the sound and receiver of the sound, and it uses that time difference in order to measure the depth, how far away whatever we're looking for is from the surface that we're looking for. So that's how we check for what's on the inside, or take a look at what's on the inside of the material here, like the thickness of the pipe, for example, or to look for blockages, and how we're able to map out the shape of the baby in the womb, or to find out the condition of your tissues and organs on the inside, and also underwater, how submarines are able to navigate and find the whatever they're looking for, or determine the depth of the ocean from the ships and the shipwrecks and all that, all based on the use of sound reflection. And the calculation of all these methods, right? That means the detection of the depth. You have to learn how to do the calculation. That's going to be covered in the next video. In the meantime, though, we've come to the end of the video. So I hope you found this video educational and helpful. Don't forget to click like and subscribe for more educational videos just like these to help you in your examinations. Happy studying!